Okay, I guess we can start. All right. So my name is Kent. I'm a assistant professor here. You're in the randomized algorithms class. It's not too late to leave. Um, so many of you may have already found that the course website is just one like ginormous PDF. We're just going to put everything in there. Um, what is there to say about it? Yeah, you'll find schedule, you'll find homework, you'll find syllabus, so on and so forth. Yeah, maybe the first important bit of information is that our TA is Tan Mei. Yeah, he took the class a couple springs ago. And one thing we hadn't quite settled, but we probably will right now. Tan Mei was thinking that he might have his office hours on Thursday, early afternoon from 1 to 2 in DSAI, which hopefully you guys will like because that's the day your homework is due. So that will be updated uh, soon enough. And okay, let me just hit the highlights of the course structure because it's kind of boring to go through everything. I kind of expect you guys to spend a little time, reading or at least giving up on the syllabus, and then coming back with questions at the beginning of class, and I'm happy to answer them. But let me hit the main points. There'll be a midterm and a final. The midterm will be roughly halfway through the class. Homeworks are like once every 2 weeks ish, although you have a homework zero due in week and a half. Uh, we have all these gimmicks, like out of all the various homework problems that you'll submit over the course of the semester, we will drop the lowest 1/5 of your score. So, if you bomb some question, it's not a big deal. Uh, a new feature of this year's course is that we have a lot of students and the same number of TAs. So right now we have 70 people registered, which is like beyond that point, it's a fire hazard in this room. Um, so we are going to experiment with some kind of like pseudo self-grading thing, which you guys might find annoying. But roughly after you turn it in, we're going to give you back a rubric, and the next week we want you to say, out of 10 points, I get this much in each category. And then, like, if you give yourself like half a point or something, just write a sentence or something. The real thing is that Hanmei is going to kind of use that as guidance to hopefully speed up the grading because 70 students is a lot for one TA. Um, Things I forgot to probably list. You can do your homework in groups of up to 3, so that should hopefully save some time. And what else? I don't remember. I should have written more. But anyway, does anyone have any questions? And also, I'll keep opening this up for questions in the next couple of lectures. Um, so you have plenty of time and opportunity. Yeah, I'm not giving you much to work with, but hopefully you'll read the syllabus. Fine. Okay, then let's do some fun stuff. Fun. Okay, so our first lecture, an introductory lecture. Uh, a little bit introductory to probability, though I'm going to probably go through these definitions quick because people don't like it when I go through them slowly. But what I really want to do is to talk about 3 algorithms and 3 problems. Oh, also, any of you have taken a class with me before has seen this exact algorithm lecture before, so I apologize, but you've also been warned. Okay, but I want to focus really on 3 algorithms, 3 problems, 3 SAT, quick sort, and a little bit of quick select. So let's get going, starting with 3 SAT. Okay, so hey, uh, all right, so hopefully everyone has seen a problem like this before. Okay, I'm going to give you a Boolean formula in conjunctive normal form. We have variables, we have clauses, and we're going to focus on the special case where each clause has exactly 3 distinct variables. Yeah, 3 SAT, kind of your canonical NP complete problem, for like the linchpin of this whole kind of like NP completeness theory, right? You can use SAT to solve anything that's verifiable in polynomial time. Yeah. So You should already know coming into this class that we probably won't find an exact algorithm to solve 3-SAT anytime soon, right? But it's still a practical thing. You may have a bunch of logical requirements or something, and you have some Boolean choices, and you just want to satisfy as many of these things as possible. Okay, so we can still turn this into a maximization problem where I give you the same input, some kind of 3-SAT formula, and say, okay, what's the maximum number of clauses that you can satisfy? And this question is interesting even if the formula itself is not satisfiable. Okay? All right, but there's a catch. This doesn't quite resolve anything. What's a sticking point with this problem? Yeah. Yeah, so let me reword that slightly. But if you could solve this maximization problem exactly, you could figure out if it was entirely satisfiable to begin with. So that actually, we haven't made any progress yet. But what we can do, right, is we can consider approximation versions of the problem. Okay, so what do I mean? There's some mysterious number of truly the best you can do. Can you get, I don't know, half as many as possible? Can you get a third? Can you get more? Can you get 1 over log n or something, right? But for some prescribed ratio, can you get that fraction of the optimum solution, right? Like you're going into a final, you're not going to get 100%, but can you get half, right? Same kind of idea. Okay, so so approximating SAT is not necessarily NP hard. That's why we're going to be interested in it. Okay, but what are some ideas for an approximation algorithm for maximizing a SAT form for those who haven't taken this lecture exactly before? Any ideas? Yeah. Okay, so this is all often suggested. So can you do some kind of greedy strategy? So what was your example of a greedy strategy? Okay, so maybe you're just going to walk down this formula and say like, okay, I want to make this clause happy, so I'm going to choose one of these three. Maybe I'll set x1 to be true and then just keep going. Okay. Any other ideas or interpretations of greedy or whatever? Yeah. Could do greedy on the variables. So for example, okay, so just say like, oh, kind of what's best for x1, right? And what's best for x2, what's best for x3? Maybe you could even, I don't know, you don't even have to do x1, x2, x3. Maybe one of those xi's, either true or false, will somehow make the most improvement at once. Maybe that's a possibility. Any other ideas? Yeah. Okay, you can try to randomly assign true or false to each one. Seems naive, but sure. Okay. Although maybe it fits the class. Any other ideas? Uh, Very good. Okay, so we are actually going to take this silly suggestion of randomly assigning variables. Okay, so this is, I think, maybe the silliest algorithm I can think of for the problem. We'll just go through every variable one by one, and for each one, we're just going to toss a coin. Okay, if it comes up heads, I'll say I'll make that variable true. If it comes up tails, I'll make that variable false. Okay, a very simple algorithm, right? One that doesn't even really look at your formula. Okay. All right. So we're gonna study this, and we're gonna show two things today. Okay. First, we're gonna show that this will get you a 7/8 approximation for 3-SAT. Okay, it'll be your first example of an approximation algorithm. And the second, it's a little more subtle. We're gonna take that randomized algorithm, which was about as randomized as one can imagine. You're tossing a coin for every choice. okay? And we're going to make it deterministic. We'll get rid of all the coin tosses, but maintain the same quality solution. Okay, good. And later on in the semester, we're going to work our way towards, we won't fully prove this. Okay, so this very simple, dead simple algorithm gets you a 7/8 approximation. What's stunning is that if you could do better than this brain dead algorithm, then P is equal to NP. Okay, so for all epsilon greater than 0, if you could do a 7/8 plus epsilon approximation on 3-sat, then you can actually amplify this and get an exact 3-sat solver. Okay, that's very surprising. Okay, so that's based on kind of an extension of the P versus NP theorem, but it's a techniques called probabilistically checkable proofs, or at least the name suggests there might be some alignment with randomized algorithms. Yeah, so we're going to try to build up some of the tools to understand this proof, although the full proof we won't do. Okay, but it's pretty amazing result. Good. So that's 3-sat. Let me introduce the other problems, and then we'll go through and we'll analyze things. Okay. Second problem we'll look at in detail is just sorting. Presumably you've all looked at sorting to death before. So I'll give you, n comparable things like numbers, and you just want to list them from smallest to biggest. Okay. So you know that you can do n log n with divide and conquer, like merge sort. And then you might also know that you can't do better than n log n. Yeah, there's these kind of, if you're in the comparison model, all you can do is compare any two elements. You can't do better than n log n. Okay. All right. So we're going to look at a randomized sorting algorithm that again is going to be very simple. In fact, many of the algorithms we have in this class will be very simple randomized algorithms, and there's a little more sophistication on the back end in the analysis. Okay, but that's a trade-off we like because well, the computer just is the one dealing with the algorithm. Okay, so okay, it's a very intuitive algorithm. You have a bunch of numbers or something, and step one, you're just going to pick one of them out of the pile uniformly at random. Yeah, just pick one of them. And then you're going to pile up everything that's bigger and then recurse. And you'll pile up everything that's smaller and recurse. Yeah, it's like a arguably intuitive algorithm. You're probably more likely to do this in real life than merge sort. Like that's for crazy people. Okay. Anything down here? Yeah, so this is called quick sort. And at least at a certain times, that was a standard sorting library in Unix. All right, good. Uh, so a picturesque version. Okay, you're going to pick a random pivot out of your array. You're going to split it into two parts. You're going to recurse, and then everything's sorted. It's very simple. I mean, this is probably a better description than the lines of code. Good. Okay, so we'll prove two things today. We're going to show that on average, it takes n log n time. Sort of kind of looks and smells like merge sort, like you'd expect. And then this will be a little more tricky. We're going to show that it takes n log n with very high probability. Okay, the probability of it being like at least 100 n log n will be like 1 over n to the 100 or something. And you can replace 100 with whatever constant you want. Okay, so it's almost certainly going to take n log n time. Okay, good. The third algorithm I want to introduce, okay, is for the selection problem. It's a lot like sorting. And again, you've probably seen it before. You have a pile of numbers or otherwise comparable things. And I give you some rank, like the median. Say, okay, find me the median number. And of course, you could sort everything and then pick out the median, but that's no fun. Okay, so you want to try to do even faster. And you may have seen, you should have seen, uh, a very clever divide and conquer algorithm that takes linear time called the median of medians. Have you all seen this algorithm? Kind of divide things into groups of 5. Okay. Right. So this is a very celebrated algorithm. In practice, it's not actually super fast, allegedly, because it's a little complicated. We're going to look at a simpler algorithm, and I guess better algorithm in practice. That's very similar to our quicksort algorithm. The first step is the same. Okay, so you're looking for the median or the rank k more generally, right? The k smallest. Pick something randomly, divide it into two piles. Everything smaller, everything bigger. So everything will get compared to your pivot. But by the time you've compared everything, you at least know the rank of your pivot. Okay. And that means, okay, if you got really lucky, this is what you're looking for. Otherwise, you know which side it should be on. If the rank's bigger than what you found, then you need to go on the right side. Okay. So whatever is the appropriate size, and maybe the rank will get updated, uh, you're going to recurse. Yeah. So if you go to the bigger side and you're looking for some like rank K and this was rank L, you want to look for like the rank K minus L. I got that right on this side. Yeah. Nothing, nothing surprising. Okay. So that's quick select. Very simple algorithm. Pseudocode makes it look more complicated than it is. And for homework, by two different ways, I'm asking you to prove it takes linear time and expectation. Yeah, and you'll probably be able to do this because it's going to be somewhat similar to quicksort, which we'll do together. So you'll get to kind of reapply what we learned. That's the idea. Yeah, and the homework gives two different ways to do it, and you're supposed to do both. All right, good. Any questions? All right, let me roll through. Um, Let me roll through some basic definitions, but I'm probably going to go really fast, unless you pause me for questions, which I'm very happy to answer. Okay. And if probability is new to you, take comfort in the fact that that's all we're doing. So if it's a little awkward today, hopefully with some practice, you'll quickly become more, comfortable with it. So let me run through it. Also give you a chance to get used to my intuition or my handwriting on me. Okay. So in general, you flip a coin, right? And I say, oh, is it heads or tails? And then what do you say? Well, say something. Yeah, you'd say heads, tails, or you'd be technical and say, I don't know, half, half, right? But the point is, we don't know the outcome, right? It's a funny question, but I think many of you would say something that like, oh, half the time it would come up heads, and I think everyone is comfortable with this wording. But if you think about it, it doesn't really make any sense. What does it mean for a coin to come up half the time heads? There's only one coin; it's not going to land on its side in all likelihood, right? But I think expression makes total sense. What you're imagining is like, well, if I kind of did this experiment in my head a gazillion times, I would expect like half heads, half tails, something like this, right? But it's totally like it's totally a matter of imagination. It's all in your head when you say it's half the time. So, all right, so probability theory is kind of based on this, right? So for any, the basic things are events. Each event has some fixed probability, some value between 0 and 1. Half the time would be 50%. For every event, there's the event of it not happening, the opposite complementary event. The event plus not happening, it should add up to 1. Yeah, those are the rules. You can start combining events, right? So if I have two different events, two different coins, I say, oh, whether I was at this is heads and that one is heads. Yeah. Okay. So and you can say, oh, you can say A and B or A and not B, and you have some Venn diagram. Okay. Uh, Now these joint probabilities have some simple rules. For example, if I look at the probability of A, there's event A happening, right? And I have some other event B. Well, when A happens, B happens or it doesn't happen, right? So I either have A and B happening or A and not B happening within the sort of A happening event. And so you see that expressed in that first equation, the probability of A is equal to the probability of A and B plus the probability of A and not B. Okay, should be intuitive. Um, The conditional probability of B given A, will be that joint probability divided by probability A. That'll be some value between 0 and 1. And if you start doing some math, you get some nice things like conditional on A, the probability of B happening plus the probability of B not happening all adds up to 1. So you kind of zone in on the universe where A happens and then everything is nice again. Yeah? I think many of you have seen this before. Now, in general, conditioning on event A happening will essentially affect B happening. If there's no effect, then they're independent, but that's generally not the case. Okay. Yeah. Good. All right. Besides A and B happening, you can have A or B happening. Okay. And you can take A or B happening and kind of break it up into three mutually exclusive events, like A and B happens, A and not B. You get it? Okay. Uh, and with a little rearranging, you'll get one inequality which seems very simple but is extremely useful. If I have two events A and B, probably A or B happening is always bounded above by the probability of A happening plus the probability of B happening. Okay, you've almost certainly seen this before. What I want to suggest right now that's so nice about this union bound is that it makes no assumptions about A or B. Yeah, they don't have to be independent for this to be true. In some ways, it's a weak inequality, but it's very flexible. It's going to be very nice because we'll analyze, big complex algorithms like crazy things are happening. And to be able to say, you can kind of pull this out without really understanding the relationship between the various events going on in your algorithm. Yeah, so some of these simple inequalities that often seem loose are in fact going to be very, very useful. Okay. So events are like things that happen or don't. You also have finite random variables that take on numbers, like the usual examples, like you roll a dice, 1, 2, 3, 4, 5, or 6, and you get some kind of quantitative analog of everything we just did. So a random variable taking on a particular value becomes like an event. Oh, what are the odds that I roll a 6? That's 1, 6. Okay. Okay. Now you can have two random variables, and then we can start talking about the joint distribution of two dice, just like we talked about two different events. Okay. Everything will kind of go through. Just like before, you know, I could say, okay, I have two random variables. What are the odds that one is this, the other is another, right? And it's not necessarily equal to the probabilities taken apart. The random variables depend on each other. They're independent, they do, but in general, they don't. Okay. Uh, right. So I guess the silly example I give is okay, if you have two different coins, two different coin tosses, then they will be independent. So if I'm looking at like heads and heads, that'll be 1/2 times 1/2. Yeah, and same with all the other combinations. So if you have two different coins, there'll be independent random variables. But of course, if X and Y were modeling the same coin, then they're not independent. You always get heads, heads, or tails, tails. You'll never get heads, tails, or tails, heads because it's the same coin. Yeah, okay. Nothing, I think you've all seen this. Good. Okay, so here's a first very useful definition. Okay, so with any quantitative random variable, we can have an average. Average in exactly the sense of the word you're used to, like batting average. Okay, but formally, we can sum up over all the little outcomes, 1, 2, 3, 4, 5, and say, okay, what's the probability that's equal to 1 times 1? The probability that's equal to 2 times 2, probability that's equal to 3 times 3, and add them all up, and you'll get the average. Yeah, the fancy term is expected value. And another very simple property, but incredibly useful, is linearity of expectation. Okay. So if I give you, a few random variables, and you want to know the average of their sum, okay, it's always going to be the sum of their individual averages. Here's two variables, but it could be however many you want. Okay. And again, this is going to have, be useful for the same reason as the union bound. We don't have to make any assumptions on X and Y for this to be true. They could be completely correlated, they could be completely independent. You get the same thing this time even with equality. And again, we're going to be looking at some like crazy algorithm and we're going to set up all these crazy variables. It's not going to make sense when you look at it in detail, but we're sometimes going to be able to just look at the averages and start separating things cleanly with this rule. Yeah, this is almost the single most important thing we'll do in this class. Okay, good. Okay, more stuff, right? You can start conditioning on certain events happening, okay? And then you get kind of equivalent definitions. You can have expectations over multiple random variables, okay, or maybe even functions of multiple random variables. So take something like this, the expected value of fxy for some mysterious function f, yeah, and we can just kind of gradually work through the definitions. Yeah, this is just kind of the definition of expectation, and uh, if we actually take this and break that down into something like the probability of y equals y given x equals x times the probability that x is equal to x, then you'll get this sort of iterated expectations. Yeah, so I'm taking expectation of multiple variables, but I can kind of focus on one at a time. Okay. Anything down here? Nope. Um, I don't know if this is very compelling, but I Googled for an example once. So I guess here's an example of the law of iterated expectations. One random variable is whether or not it rains tomorrow. The other random variable is whether or not it rains today. Okay. And you really want to know, I guess you really want to know if it's going to rain tomorrow. If you know it rains today and you have some kind of mechanism to estimate whether it rains tomorrow, depending on whether it rains today, uh, then you can estimate if it rains tomorrow. Okay, it's not a great example, but oh well. We'll use it later in the lecture. Okay, one last boring math thing will be Markov's inequality. Okay, so Markov's inequality is about what is the probability that a random variable that's non-negative greatly exceeds its expectation. Okay, so it takes any non-negative random variable. What's the probability that it's 10 times its expected value? So alpha is 10 times expected value of x. Okay, then you'll get 1 over 10. Okay? But this should not be too surprising. It's just saying, uh, at most half of something can be twice as big as the average. Otherwise, it won't all add up if it has to be non-negative. Okay, so this is like total common sense. At most 1/10 of x can exceed the average by a factor of 10. Okay, good. All right, I think we're out of yeah, it's not so hard to prove this. Okay, good. So that was my speed run through some basic definitions to get us started, but obviously I went fast. So is there any questions? I'm happy to go back. Okay, then let's analyze some algorithms. All right. Okay, so the first thing we're going to do then is reset. Remember, I have 3 variables for every clause, and we're looking at this simple algorithm that just flipped a coin for every variable, setting it to be true or false. Okay? And we first want to show that it gets you a 7/8 approximation. Okay, so let's kind of go through this slowly with just some simple examples to get warmed up. Okay, so suppose I only had one clause in my formula and I'm just flipping coins. Yeah, in which case your algorithm isn't that great because you could probably do better on one clause, but still. Okay. So what are the odds that I satisfy this one clause C1? What's the probability of E1 in this notation? Yeah, because yeah, okay. So it's a little easier to actually focus on what are the odds that I don't satisfy the clause. Okay. And in this case, I would need x1 to come up tails, x2 to come up tails, and x3 to come up true. They'd all have to happen, and all those coin tosses are independent. There's a 1/2 times 1/2 times 1/2, which gives you a 1/8 chance of this not working. Yeah, so probability of not E1 is 1/2 times 1/2 times 1/2. It'll get you 1/8. So the probability of satisfying that clause. So I'm only doing this slowly because it's our first time together. Is 7/8. Yeah, nothing special. You already knew how to do this walking in the door. Okay. All right. Good. So let's look at. Mhm. Okay, yeah. So the probability, so E1 is satisfied in this bar. Okay, so this is a probability that E1's not, that C1 is not satisfied, so not E1. So those are ors, x1 or x2 or not x3. So as a result, there's actually many ways to satisfy it. Like if x1 is true or x2 is true or x3. So, but to not satisfy it, you need all of them to come out false. And that's why it got flipped. Okay. Okay, so good, good. All right, now let's just look at two clauses. This is the next kind of simple case, okay, where all the variables are disjoint, distinct. Okay. All right. So I can say, okay, so yeah. So what's the probability that the first clause is satisfied? Guys, I've already kind of done this, right? So for both of them, the probability of them being satisfied is 7/8. Okay. And if we just wanted to kind of compute the average, sort of based on the definition, right? I would want to do, okay, what's 2 times the probability that they're both satisfied, E1 and E2, plus 1 times, I guess, the probability that one of them satisfied, E1, but not E2, plus 1 times the probability of not E1 and E2. I'm satisfying just the second clause. And then I can leave out the 0 times whatever, because that won't add anything. Okay. Okay. So let's just look at this then. What is the probability of E1 and E2? That was fast. Okay, 7/8 squared. But in particular, because they're independent, we can break this out into a product. Yeah? Or there's what? Oh, these are supposed to be ones. 1. Uh, yeah. Okay, that's a 1 now. I set the rules. Okay. All right. So these are independent, so they just break out into a product. So you get 7/8 times 7/8. And then what would this be? This would also be independent, so it's going to break out into a product. 7/8 times 1/8. Okay, so this will be 7/8 squared. 7/8 times 1/8. I guess 1/8 times 7/8. Where implicitly, I mean, I'm skipping over the part, I guess I'm writing it out now, where because they're independent, we can break it out into a product and plug these things in. Yeah. Okay. Can anyone quickly do math in their head and tell me what this comes out to? Just add, multiply and add these things. Yeah. 7/8. Anyone else get 7/8? 14/8? Okay, also known as 7/4. Anyone else get 7/4? Okay, that okay, good. All right. All right, simple enough. Again, I think everything is still within everyone's comfort zone. All right, let me just do a small twist. Two clauses, one variable in common. Okay. So, okay, so this gets like if we can just try to calculate, for example, probability E1 and E2 happening, right? That was sort of the first calculation we did last time. Okay. How can we and just one variable in common. It's not that complicated, it's just two clauses. Yeah. Ah, okay. So good. So I can do E1, E2, condition on x3 being true times the probability that x3 is true, uh, plus the probability of E1, E2, condition on x3 equal to false, times the probability that x3 equals to false. Okay. It's more impressionistic by the end. Okay. Okay. If x3 is equal to true, what are the odds that both clauses are satisfied? One, I guess, right? Because they both have x3, so you'll just be happy. And then what's the probability that x3 is equal to true? Half. Okay. Now, what happens when x3 is equal to false? So when x3 is equal to false, it's going to look like this. Okay, so it's actually going to get you two different clauses. So, if we did this slowly, you could write this as E1 given x3 equals to false times the probability that E1 given E2 given x3 is equal to false. Something like this, right? Okay, so, and then what would one of these be? Now you just have two variables. Think I heard it? Maybe I didn't. X3 is false. What are the odds that we satisfy 3/4? Because now just two coin tosses, so you only lose if you get tails and tails, or I guess tails and heads in that example. So 1/4 of the time you lose, 3/4 of the time you win. Okay, so you'll get 3/4 times 3/4. Yeah. Okay, so what would that even? Where does this all come out to? So we have like, looks like we have 1/2 from the first kind of term plus 3/4 squared times another 1/2. All right, what is this? I'm honestly asking. You made something up, I wouldn't know. 25 over 36. Anyone else get 25 over 36? Over 32? Okay, you seem to have conceded on 36, so we'll go with this. Okay. All right. So, okay, good. So it took the whole whiteboard to figure out just like one of these. So we only have like four more terms left or something, right? Okay. And that's only two clauses with one common variable, right? What if I gave you three clauses with common variables, right? If we did it this way, like we would be here all day. Okay. Okay. And then, our real goal was to do like M clauses with however many variables, right? I mean, we don't even know. The whole point of SAT, it's kind of inscrutably complicated, right? That's why we don't have any good algorithms for it. Okay, good. So, uh, okay. So trying to do kind of a fine grain analysis of any of these kind of complex combinatorial things is very messy, right? So that's the basic question that we confront, and we'll be confronting all this lecture and at some level all class. Okay, so how do you analyze some kind of randomized mechanism with a combinatorial explosion of possibilities? All right, this will come up all the time in algorithms. All these different things can happen. right? Mysterious interactions. How do you analyze, something that's kind of arbitrarily complicated? All right. So the big idea in this lecture is that we're only looking for the average, right? I just want to know the average number of clauses that are going to be satisfied. And that's going to make our lives much easier. Okay. But if you don't kind of take this step, you're hopeless. This is really the only idea in this class. Okay. So what we do, and you'll do this a lot for other problems, is we first just set up some simple random variables. So for every clause, I'll make some variable yi that tells me whether or not it's satisfied. Okay. So y10, that'll be the 10th clause. It'll be 1 if I satisfy the 10th clause, and 0 if not. Okay. So what we're interested in is the sum, right? Summing up the yi's will tell me, how many clauses were satisfied. Okay. Now, let's just look at one clause. What's the expected value? What's the average of one of these random variables? 7/8, right? That's what we did at the beginning. And that was very straightforward because you don't satisfy if you just get all tails. Okay, so it's just 7/8. So now, when we start looking at what we're really interested in, what's the expected number of clauses I satisfy, right? I'm just plugging in the random variables here. Yeah. And now what? It's like the one. Okay. So here we get to use linearity of expectation, which looks very simple. I'm just going to put the e inside the sum, right? But the average of the sum, which is what I'm looking for, is the sum of averages. The average of the sum is the sum of averages. Okay. And now what comes at the end? Now we just plug things in and you're done. Yeah. So, if you had tried to analyze, these things kind of individually and map things out, it's completely hopeless. But if you look at the average and you kind of, you know, get comfortable with this style of thought, okay, it's a one-line thing. Yeah, we never had to do a harder calculation than tails times tails times tails. Okay, okay, good, good. All right, so that's the 7/8. Yeah. Okay, so you're asking a question about concentration, which will certainly be a topic in the future. Um, so mm, okay, so mm, yeah, a little bit of spoiler for the future, but that's okay. When you have lots of independent events, like you guys probably know things like the central limit theorem or something, right? If you throw 1,000 coin tosses, they're all independent, you'll get quite close to 50%. You won't get exact, of course, but you get pretty close to 50%. Because at some level, okay, the average is 50%, and it's very hard for independent coin tosses to kind of gang up and move away from the average, right? You have to get really an unlucky streak. And we'll quantify that in 100 million different ways. But that doesn't quite fit this situation. Why? Does anyone want to? Yeah. Yeah, there could be lots of dependencies on I mean, I could have taken the same clause and just repeated over and over and over and over again, in which case that means you'll get all m of them 7/8 of the time, and none of them 1/8 of the time. Yeah, so without knowing any structure about the formula, we can't make any strong statements like it's often going to be close to the average. Yeah. Huh? Yeah, not it is supposed to just give you an impression of the wrong way to do it, so it's not too terribly important, but okay. All right, so yeah. Okay, so if you focus on averages, suddenly, yeah. Yeah, so there's some yes, right? So this makes sense. This is what we're looking for. Expect number of clauses satisfying. And for every clause I've made a random variable yi. So when I sum up over the yi's, that's 1 point for each clause. Other questions? Yeah, got it. All right, so I promised that once we did part one, we're going to try to take that completely random algorithm and make it deterministic. Okay, so let's do that. Oh, okay. There's a slide for ideas. Any ideas? You don't know the answer? Wrong answers only, I guess. Yeah. Can you do it greedily? Uh, okay. Uh, well, the answer is no, but I don't have like a great counterexample in mind. But we're going to do something inspired by a randomized algorithm, though. Is there anything that we just did that might inspire one with no coin tosses? It's fun to think about, even if you don't know the answer, so that when I give the answer, you're more impressed. Yeah. You can assign the first half of the variables to be true and the second half to be false. And would that be similar? Uh, that can't possibly be right, but like, it's a thought. Any other, just for fun, funsies? Yeah. Better what? Can you find variables common to all the clauses? What if you don't? Well, okay. So something like, can you find a variable that's in all the clauses, but there might just be no variables that are in many clauses. I mean, there's a number of heuristics one can propose. If it's easy, then can we easily solve it or something like this, right? But yeah, pseudo random. That's a big word. Is there anyone here taking pseudo randomness? Well, you should. But anyway, it's offered tomorrow. Anyway. Oh. Uh. Okay, well, maybe first I'll explain. Pseudo randomness is a field where they try to limit the amount of randomization. Where in extreme, you might be able to get rid of randomization altogether. But an example that will come up in future lectures is like, like hash functions, right? They often only need a limited amount of randomness to get the properties we need. So you don't need like a fully random hash function. So that's kind of less randomness than you might expect going in. But there's a lot more to this field than hash functions. Um, well, that would also not necessarily eliminate the randomization altogether. But in any case, we're going to do something kind of more direct, more from first principles. Yeah. Yeah. It's yeah, so a trick that comes up in pseudo randomness is that if you can get the number of random bits you use down to log n, then you can actually just enumerate all the possible coin tosses. So if you can get this algorithm down to log n coin tosses, you will also basically have a deterministic one. Yeah. Oh, well, first of all, okay, if the number of true is significantly more than the number of falses, what does that mean? Yeah, so I think this still will fall into the category of if your formula is nice, then there are nicer things we can do. But in general, we can't necessarily expect this. So it may be well, one needs to be careful. It's quite possible that, for example, xi appears in the true form much more than false. But for some reason, the clauses it appears true in are very easy to satisfy for other reasons, and you want it to set it to false. Right? It's not so obvious, is all I'm suggesting. Okay, anyway, well, without further ado, okay. So here's the approach. This is the same start from before, the same yi's. And it's going to be convenient instead of rewriting the sum of yi's all the time to just have a variable z. So z is the sum of yi's, that's the number of clauses being satisfied. Okay. Now let's just peel apart at the expected value of z. Yeah, so this is one of those rules from before. The expected value of z, I can condition on x1. Okay. Half the time x1 is true, half the time x1 is false. Kind of very simple, right? And we know the expected value of z is pretty good. It's 7/8 m. Okay. So this is pretty good. This is an average of two things. Okay. Well, what does that tell us about one of these two choices? One of them's got to be good. If the average of two things is good, then one of these two has to be at least the expected value of z. Okay, whatever is the bigger one. Okay. So one of these two choices, right, conditioning on x1 equal true or conditioning on x1 false is good. Okay. So how can we make use of that algorithmically? Right now, that's just kind of like a math statement, right? How can I make this useful? Yeah. Try both of those. So what does try both of those? But first of all, you're trying setting x1 to be true or trying x1 to be false. Okay. So one of these two have to be good. So let's say you want to figure out this value. So you want, in your words, you try setting x1 to be true. What does that really mean? What's your computer going to do? Oh, I want to see how x1 equal true to be, right? But you want to somehow evaluate this. Yeah. Yeah, you can first look at the number of clauses that are satisfied by x1 to be true. So those you already get a point for, but there's some stuff left, right? You need to figure out this whole quantity. Yeah. Okay, so good. So one of these values are good. You're trying to figure out which means you want to be able to evaluate these quantities. So if we look at the x1 to be true, right? Then again, by using linear of expectation, you just get the sum of conditional expectations, right? And each of these are pretty easy. So if some clause has x1 to be true, then you just get one. If it doesn't have, if it has x1 bar, right? Then this will go from like 7/8 to 3/4 or something, right? And the remaining ones that don't have x1 in either form will still be 7/8. But the point is you can easily calculate it. This is just like a loop on your computer. Yeah. So the fact that you can also evaluate the expectation explicitly lets you take this, simple kind of conditional observation and turn it into an algorithm. Okay. So good. So you can just compute which of the two values is better and decide. And there was nothing random. You didn't like simulate this, which you could have, but right. It would take a while and be small errors. You can just get the exact answer explicitly without flipping any coins. It's just a thought experiment. Okay. And now you can imagine doing that, for all the variables. I've set the first 10 variables. I'm on track to get 7/8. Now I'm on number 11. And we'll do the same thing, right? It gets a little more verbose because, we've already have some conditional variables, but here's the first 10, and now I'm conditioning onto making the 11th either true or false. And I can evaluate both of these values explicitly. Yeah. Yeah, I mean, I think teachers aren't supposed to call things naive, but like this is also called the method of conditional expectation. So often, this is a generic technique that could be useful. Okay, but it's very simple. It's just kind of understanding conditional expectations. Yeah. Is it kind of like binary searching? I would argue it's not doing binary search. It's just deducing. Uh, but I'm not sure if that's a full answer to the question either. Yeah. Ah, okay. So you could try to think of this as a greedy algorithm, but using some kind of like proxy function to evaluate your choices. So it's not greedily trying to satisfy everything at once. It's greedily saying, if I set this to be true and then I continue the random experiment, would my average still be good? Yeah, so you can argue it's greedy. But the point is, what is that metric you're chasing after? Yeah. Or it won't decrease. Yeah, so you're not guaranteed anything in the worst case. Yeah. So in the worst case, that means that either coin toss would have been fine. Yeah. Yeah. Greater than or equal. So all you're guaranteed is that one of your two choices will be at least as good. Maybe they're both equally good. But you'll end up, you'll keep maintaining the 7/8 M average until there's no randomness left because you've conditioned all the random variables. Yes, as we keep conditioning. So conditioning this variable is like setting it to be true, making that decision. There might be another slide. Let's see. No? Okay, we'll stick here. Yeah. Yes. Yeah, the world is a peculiar thing. All these things can be true. It's disappointing, but it's true. Ah, yes. Yeah. So if either of these was like worse than 7/8, then you get an equally good gain on the other side. Yeah. But so what do we know is true? We're guaranteed at least 7/8 M on the algorithmic side. And on the other side, we know that anything strictly better than 7/8 is NP hard. But these are all kind of worst case things, right? So yeah. Uh, So what's surprising maybe is that kind of this silly day one algorithm is somehow best possible if P is not equal to NP. And that's the thing that I don't have a short answer for. Just something we sit with. Yeah. Other questions? Oh, we should make haste. Okay. All right. Let's do quick sort. Okay. Again, you probably have seen this before. The algorithm, pick something, split it into two files, recurse on both sides. Yeah, simple enough. Okay, we first want to show it's going to take n log n time on average. We'll do it quickly. Okay, so if I wanted to do our usual kind of recursive analysis, yeah, and if I wanted to write down a recurrence, what might it be? So maybe I'll use k to represent like the rank of the pivot. That makes sense? Any suggestions? Yeah. So on to kind of compare to the pivot and split things up. And then on one side, you have, like k minus 1 elements. And on the other side, you have n minus k. Yeah. Okay. And then where k is some kind of random thing. Okay. Now, what would be ideal for k? Yeah. Yeah, some constant, but what's even the best one to make? N over 2, right? If you could get right in the middle, then you get something that looks like merge sort. Yeah, 2 halves plus O(n). Okay. What's the worst? Yeah, you get some, you get like the first one or the last one, and you get like t of 1 plus t of n minus 2 or something. Yeah, and then n minus 3, and you just keep unrolling and unrolling, unrolling. And what would that come out to if you kept getting unlucky? It'll come out to like n squared. Yeah, because you get n plus n minus 1 plus n minus 2 plus n minus 3. All right, so that's the basic situation we're in. Ideally, it'll take n log n time. But in the worst case, it's certainly not impossible that you'll get n squared. Yeah. And then you could consider all these things in between. Like, what if my first pivot's good, my second pivot is bad? How does that compare to if my first pivot is bad and my second pivot's good? I don't know, right? It can get complicated. Okay, so yeah, I'm gonna jump a little to the punchline here. Our saving grace again is that we don't have to map out all the running times and stuff. We just need to calculate the average. Okay. And there's a swift way to do this. So, okay, expected running time of quicksort. We're going to do something that's kind of similar to what we did with SAT. Okay, but it's okay. Okay, so what we're going to do is we're going to make a random variable for every 2 elements in your input. And we're just going to worry about whether or not those elements are compared to each other. Okay, if the rank I element is compared to the rank J element for all possible I and J. That's a 1 if they are, 0 if they're not. Okay. So the sum of xij's is the total number of comparisons made by the algorithm. That's basically the running time. Yeah, if we think about the algorithm, the number of comparisons is essentially the running time. Okay, so we just want to analyze the number of comparisons in expectation. Okay. All right. So we want the average running time. What's the first thing we should do? We're going to use linearity of expectation. Okay. So I can take this big sum, which represents some complicated algorithm, good pivots, bad pivots, all sorts of crazy stuff happening. Okay. And by linear of expectation, I only have to focus on one of these terms at a time. Right? Think of how much work that did for you. At the beginning, you're like, oh, what's going on in this crazy algorithm, dynamic algorithm? First choice is good, first choice is bad, who knows? Yeah. And then you get it down to something that says, well, just worry about 2 things. If you worry about 2 things and add them up, you're good. Yeah, that's unbelievable. Okay, so, all right, so what's the expected value of xij? 0, 1 random variable, so that's also the probability that's equal to 1. Yeah. So I'm just trying to figure out what are the odds that the 10th smallest is compared to the 100th smallest. Okay, something like this. Okay, because here's like a little picture. Okay, so what is the probability that the I smallest is compared to the J smallest? How can I think about that? If I can just figure that out, then the rest is just tallying things up. Yeah. Yeah, so one of these have to be a pivot in particular before. So let's say a pivot gets chosen to the left of I. That doesn't say anything because they'll kind of end up in the same subproblem. The game continues. Same if I get a pivot over here. If I get a pivot in the middle, strictly between them, I and J will get split up. They'll never get compared with each other. So in particular, I need I or J to get picked as a pivot before anything in the middle. That's an if and only if. Okay. And what are the odds of that? Yeah. All right. So there's a numerator and denominator, right? So what are the odds that I pick I or j? How many? What's the numerator? Just two, I and j. And then what's the denominator? Like j minus I plus one. Okay. Don't hold it against me if I'm off by one. Okay. So they have to be selected for anything in between. That happens probably 2 over j minus I plus 1. Okay, so that gives us this term we're looking for. Okay, good. Okay, so that was our setup, right? And now we just do a little bit of math. Yeah, linear expectation, we did that before. Now we're going to plug some stuff in. Okay, so I'm just summing over all the choices of I and j, just 2 over j minus I plus 1. Okay, for this one, it's helpful to rearrange the terms. I don't know why I didn't write that originally, but anyway. Okay, now j is on the outside and I is counting up from 1 to j. Okay, and what's one of these terms on the right? It looks like 2 over 1 plus 2 over 2 plus 2 over 3 plus 2 over 4 plus 2 over 5 plus 2 over 6 plus 2 over 7. What does that? A log. Yeah? Okay, something like this. Okay, so you get like n log n. Okay. All right, any questions? All right. I think the key part of this, which I kind of went through quickly on account of time, is A, to realize you're doing the averages and then setting up those xij's correctly. Once you've kind of pinpointed the random variables that break everything down for you, then it wasn't so bad. Okay, that first step though is kind of conceptually tougher if you're not given any hints. Okay, good. So I think we're going to make it and be able to do the second part, which will probably be the most technical thing we do today. Okay. All right, so you've now shown that quicksort will take n log n time on average. Okay, with some linear expectation trick and this clever observation about choosing the. Did I say something wrong? Everyone's looking at quicksort. I don't know. Anyway, all right, n log n time on average. Now you want to show that it's going to almost certainly take n log n time. Okay, which also may be a style of analysis uh, you haven't seen before. Okay, so this proof is actually quite tricky, although it's not too complicated in hindsight. So what we're going to do is for each element, so an element is going to kind of appear in a bunch of subproblems, right? There's a pivot, and that element goes over here, and it goes over there, and it goes over here, it goes over there. So it's in all these subproblems from top to bottom. Okay, so for each element, I guess this random variable d sub e, the depth of e, will be kind of how many subproblems it appears in before it's like chosen as a pivot, or subproblem only has one variable, it's effectively a pivot. Okay, and each time an element appears in a subproblem, it gets compared to the pivot. Okay, and so if I sum up the DEs, I'll actually kind of recapture all of the comparisons made by the algorithm, just counted in sort of a funny way. Okay, because each time an element appears in a subproblem, it's going to contribute its comparison with the pivot. Make sense? Okay, so I want to try to analyze this sum of DEs, and the claim we're going to show is that for every DE, the odds of it being in way more than log n subproblems. We're expecting like an average of log n for things to add up to n log n. Let's say 32 times log n. 32 is chosen a little arbitrarily. Is say 1 over n cubed. Something polynomially small. I could have doubled 32 and made the n cubed, n to the fourth or something. Yeah. Okay, so why would that claim be helpful if we want to show that it's almost certainly going to take n log n comparisons in time total? If that were true, where would we go from there? Suppose I told you every element was in it. Y- Yeah, so let's go through what we need one key buzzword, right? So okay. All right, so okay, so you want to show that all of them have at most depth log n or something. Okay. And so there's going to be some exactly what you said, but sorry. Oh, okay, union bound. Okay, so by the union bound, the odd of any of them being too deep is that the odds of all of them or any of them kind of added up being too deep. Okay, and each of these we showed is extremely small, 1/n cubed. I can drop in 1/n cubed into this sum, multiply it by n, I still get 1/n². So once you get things kind of polynomially small, then you can start union bounding, in a very lazy fashion. Yeah, again, union bound is great because I don't care that they're not independent. I'll just give that up. But I've driven down this probability so low that I can afford it. Okay, good. Okay, so that will give you your sum. Okay, so we just have to prove this claim. Okay, so I just want to show that for every element E, it's at most 32 log n with very good probability. Okay, so we're going to fix a particular E and just try to prove one of them. Okay, see how this goes. Okay, so we're going to focus on one element E. The first subproblem, it has n other elements in it. The next subproblem has fewer, and then fewer, and then fewer, and then fewer, and then fewer. Okay, so I'm going to make a variable xi to count how many elements are in its subproblem in the ith round. Okay, so and I'll say once it's been selected as a pivot, it'll just be 0 afterwards. Okay, so that's good. So that means that the way things are set up, this depth is at least say 10, only if in the 10th round there's at least one element in the subproblem. Okay, all right. Oops. And now we just want to upper bound expected value of xi, or that's going to be one of two steps. Okay, so what does the expected value look like? Okay, so I'm going to say that a pivot in a particular problem is good if it's somewhere in the middle 50%. That means excluding 25 on each side, right? So if I get a good pivot, in E subproblems, how many elements am I going to split off? Split off, so okay, I think I've heard a bunch of numbers. 1/4, right? Because in the worst case, you're going to be on like this 3/4 size of good. So, all right, so now let's just look at x1, the first subproblem, right? Or maybe x0 is n. Eh, okay, let's just see how it goes. Okay, so if I look at uh, okay, I want to know what's the expected number of elements in that first subproblem, not including the 0th one, which is like n or something. Okay, so half the time you get a good pivot, half the time you don't. I think I'm missing a 1/2 there. Okay, but if it's a good pivot, then how many elements do I expect in that subproblem? Oh, okay. Keep it going. Okay. So you're going to get 1/2 times 3/4 n. And the other half, you got a bad pivot. In the worst case, there's n. So these are just kind of loose upper bounds. Okay. But you're going to get 7/8 n in expectation. These are kind of loose upper bounds. Okay. You could do the same thing in general, but you have to condition appropriately. So conditional on you know that the x1 you're starting with n. 10 problems in, you're starting with something. You don't know, but you will condition on that. And otherwise, we'll do the same arithmetic. Okay. This is again conditioning on how many there was in a previous problem. 1/2 times 3/4 that number, or 1/2 times that number. Bad pivot, okay, you get all of them. Good pivot, you got rid of at least 1/4. So you get 7/8 again. Okay? Promise this is going to go really fast. And now we can just start unrolling, right? The first one's n. The next one will be 7/8 n in expectation. Okay, base case not interesting. Come on. Okay. Ah, this is all fancy for unrolling. Okay. I'm looking at the 10th problem. A condition on the 9th problem. 7/8 times the 9th problem. And by induction, the 9th problem will be like 7/8 to the 9n. So then the 10th problem will be 7/8 to the 10n. Okay. The expectation of these things is plummeting, right? You're expected to chop off at least 1/8 of the elements each time. Okay. So what does that mean? When you start getting to like 32 log n or something, and you start plugging this in, right? Like 1 minus 1 over 8 to the k. And then we're going to use an inequality that maybe you haven't seen before, but we're going to use so much that you'll never forget it. Okay, it's 1 plus x less than equal to e to the x. Okay, it's just kind of drawing a line, and okay, I won't do it for time. We'll do it later. Okay, e to the negative 4 log n. Okay, I'm just plugging in numbers and canceling terms and keeping it moving fast because we're out of time. And you'll get 1 over n cubed. Okay. Good. All right, we just have one step left, and then we're done. Okay. Okay, so now you want to know where are the odds that a depth at least k, where k is 100 times log n or something. Okay. And this will be, what are the odds that there's at least one element, okay, in that case subproblem. And all you know about the case subproblem is the expectation is super small, like 1 over n cubed. Okay. So if I have a random variable that's non-negative, the expectation is like 1 over n cubed. I want to upper bound the probability that's at least 1. It's a random variable that should be super duper small. On average, it's like 1 over n cubed. I'm saying, what are the odds it's at least 1? Okay, we can use Markov's inequality. Okay. Here, alpha is just 1, so it looks a little simpler. Yeah, so it's just the expected value of xk, which you already showed is super duper small. Okay. We plug that in, you get 1 over n cubed. Okay, I think I've abused your patience enough, but that was the last step we needed to ultimately show n log n was high probability, going back to what we did at the beginning. Yeah? Well, happy to answer questions, but I've used up time, so we'll end there. Okay? All right. See you next time.